The first hour, I'll split the time with Chelsea. I'll talk about utilities, and Chelsea will look at how you might infer human utilities. Okay, so let's go back to the basics for a moment here. Let's say you're a robot. There could be many things you could care about. Maybe you like ice cream, maybe you like candy, maybe you like watching cat videos, maybe you like watching dog videos, maybe you like playing with balloons, getting flowers, and so forth. And so the question here is fundamentally, imagine the robot or a person cares about all of those things. How to optimize their behavior? What we've been doing so far is we've been saying that somehow, even though underlying there might be so many things we care about, somehow we can condense this into a reward function. And that reward function captures everything we care about in terms of watching cat videos, dog videos, eating candy, ice cream, and so forth. And then not only have we said that you can capture it in a reward function, we've also said that it's okay to look at the expected reward. Okay? So those are two pretty strong assumptions that we've been optimizing expected reward, even though there could be many, many things you might care about. And so let's think about that a little bit in the next 15 minutes. So what we've been doing is maximizing expected utility. You could ask yourself the question, why should we even average utilities? It's another thing you could do. You could say, maybe I should reason about worst case. What's the worst case scenario that could happen to me under a certain policy? And then pick a policy such that the worst case is the best among all worst cases I could have by choosing across policies. That has its issues, though. For example, if you then see a cute little bunny, you might think it's a vampire bunny and get really scared because there's a tiny, tiny little probability that you should be scared of this bunny. And so, effectively, when you optimize for the worst case, you probably end up staying at home doing pretty much nothing all the time. Because once you leave your house, there's always a probability something would go wrong that's pretty bad. So worst case doesn't really work. So let's go back to maximum expected utility. What we call a rational agent is one that chooses the actions that will maximize expected utility given the knowledge of the world the agent has so far. Okay? So, but then this leaves some questions. Where do these utilities come from? How do we know they even exist? How do we know that averaging even makes sense? And what if our behavior cannot be described by utilities? What do we do then? Okay, so utilities, what are they? Utility is same as a reward function. It's how much you care about an outcome, how good it is for you. So it's a function from the state of the entire world to some number quantifying how good that state of the world is for you. If the world is a little narrow here, for example, you might have state of the world where you get an empty cone, a cone with 1 scoop, cone with 2 scoops of ice cream, and you might have preferences between those, meaning that the utility value is different between those 3. So in some situations, it's relatively easy. If you have, let's say, a game of chess or Go, you could have a -1 if you lose, a +1 if you win, and that probably captures the situation well. Now, here's a very interesting theorem that we'll look at in a moment. It turns out that any rational preferences, and I haven't defined rational fully to you, but any rational preferences can be summarized into a utility function. So that theorem is suggesting that optimizing expected rewards could actually be a good thing to do, assuming what we're optimizing for is somebody who has rational preferences. You could also ask, could we just hardwire utilities and let behaviors emerge? So why do we hardwire utilities rather than behaviors? Imagine you have a robot that needs to do something. Maybe you should just say, this is what you should be doing, rather than say, optimize this reward. It's tricky to prescribe behaviors because that requires a lot of detail about what the robot needs to be doing, whereas often specifying something like, I'd like the floor to be clean, is a very easy thing to specify. And so it's more convenient to say I want the floor clean than to describe what the robot behavior is that needs to happen to get the floor to be clean. You could also wonder, why don't we let the agents pick their own utilities and maximize their own utilities? Sometimes people do that, like our utilities are in our brains and we kind of pick our own utilities and then optimize for them. But the tricky part here is that if we let the agents pick their own utilities, and then we have no control over them anymore. And we can't get them to do what we want them to do. We need to give them the utilities that we care about such that they optimize for what we care about. And if they really can optimize whatever they want themselves, they could just decide they optimize some number in their memory and make that as high as possible, and that's very easy to do, and so it's not really what we want. Okay, so a lot of considerations here. So let's look at an example. Let's say you want to get ice cream, and you could choose between getting a single scoop or a double scoop of ice cream. Let's say I'm treating you. You're coming to the ice cream store with me, and I tell you can get 1 scoop or 2 scoops. I'll pay for it. Okay, this robot went with me, got a scoop of ice cream, looks pretty happy. But how about if you got 2 scoops? Well, it turns out the situation is trickier when you get 2 scoops. What could happen is that when you have a tall tower of ice cream scoops, you drop it, and you lose your ice cream, and you're not happy. Or you don't get any trouble, you have your 2 scoops, and you're extremely happy. Now, it's pretty clear from the faces of these robots that this is the worst case, this is this medium case, and this is the best case scenario. But to decide what to do, ask for 1 or 2 scoops, actually depends on the probability of the event here, how this splits up. If it's guaranteed to go here, well then certainly you pick get double. But if it's a probability that's strictly between 0 and 1, then actually you need to be able to quantify how much you want each of those and quantify how much you want this one, be able to compare what is the right option to take. And so what we see here is that once probability comes into play and things are not certain, you need to do more than just be able to order your preferences. You need to do something where you can compare probabilistic trade-offs between things. Okay, so that we'll call a lottery. So let's say there is prizes A and B, then the lottery L over A and B has probability P of U ending up with A, for example, losing all the ice cream, and probably 1 minus P of ending up with B, which is having still the 2 scoops of ice cream. So notation we'll use is we'll say, this means A is preferred over B, and this means we're indifferent between A and B. Okay, so we could have just a single prize, or we could have a lottery situation. The lottery really means a probabilistic event. It doesn't mean like playing the lottery, the California lottery or something like that. It means that there is just this probabilistic event that's about to happen between 2 outcomes that you might get. Okay, so now let's see how we can ensure rationality and see how we can tie this back into what we've been talking about. So we can put forward some axioms that we want our agents to satisfy, and if not, then we call them not rational because it's just seemingly stupid to not satisfy those axioms. First one is axiom of transitivity. If we prefer A over B and we prefer B over C, then we should also prefer A over C. Okay? Seems reasonable. In fact, if you run into somebody who doesn't satisfy this, there's a game you can play. So if somebody has something that doesn't satisfy this, if they prefer B over C, well, let's say you have B and they have C, then you can give them B in exchange for C. And because they prefer B, you can also get a little bit of money with it, because you can get C and a little bit of money in exchange for B. If they then also prefer A over B, so those are the first two and that we're looking at here, they prefer A over B, then if you happen to have A handy, you can give them A and get B in exchange, which you just gave to them, but they'll give it back to you and give you a little bit of money to give it also back to you in exchange for A. If now ultimately they actually say they also prefer C over A, which allows you to then go again and keep going around in a circle, constantly exchanging A, B, and C between the two of you, and constantly you getting money for every exchange that happens. So clearly we want our agents to be satisfying this axiom, otherwise you deploy this agent, it could cost you a lot. There's more axioms we want them to satisfy. Orderability, A has to be, either A is better than B, or B is better than A, or you're indifferent between them. You need to choose between those three. Transitivity we just covered. Continuity. This is where lotteries come into play. If A is better than B is better than C, then there must be a probability P such that the lottery between the two extremes, A and C, is equivalent to B. So there exists a P, not for every P, but there must exist some P, some value between 0 and 1, where there's ambivalence between these two situations. Substitutability, if you're indifferent between A and B, then if there are lotteries that involve A and B, you're willing to sub A and B inside those lotteries too. Monotonicity, if you prefer A over B, then if you have a lottery between A and B, with some probability on A, some probability on B, then if you increase the probability that you put, decrease the probability you put on A, then that should be a less preferred lottery than the one where you had higher probability on A. So all of these make a lot of sense. There's a theorem that says these preferences imply that if you have these preferences and you behave according to those preferences, then your behavior is also describable as maximizing expected utility. So you have this, you're approved as a rational robot. Let's make this a little more concrete rather than just a stamp. There's a theorem from 1931. Given any preferences satisfying these constraints, there exists a real valued function U such that U of A bigger than U of B if and only if A better than B. And also, if you have a lottery you're considering, the utility of the lottery is equal to the weighted average of the utilities of each of the outcomes. So this is very interesting. The first part is maybe fairly straightforward that this would be true as long as there's no lotteries involved, but this is very interesting. This means that averaging according to the probability of the outcomes is the right thing to do, assuming the reward function matches your utility function. Okay, so we now know that maximizing expected utility is a well-justified thing to do. You could have agents who are rational that don't know about probabilities and don't know about utilities, but they just have a hard-coded correct behavior or something that happens to be aligned with it. But the interesting thing here is that this justifies everything we've been doing if we want rational agents. Let's take a look at human utilities. How do you infer those? So utilities are numbers associated with lotteries or outcomes. So you can normalize them between 0 and 1. Then one way to measure utilities is to have some kind of unit, micromort. It's a 1/1,000,000th chance of death, which is useful for paying to reduce product risks and so forth. Some people here talk to me about healthcare applications of RL. This could be your unit right there in your reward function. Another one that would fit there, maybe a little more positively phrased, but in some sense the same thing. Quality-adjusted life years useful for medical decisions involving substantial risk. Okay, so now you don't need to put it between 0 and 1. You can always rescale your utility function and everything will be the same because expectations and rescaling by a positive number and adding a number will not change things. But scaling between 0 and 1 is one reasonable thing to do. Keep in mind again, if you never have lotteries, then it doesn't really matter so much what the numbers are. Just think about an ordering. But once there's probability involved, you need the numbers to be precise because you're going to average them and based on that make decisions compared to other numbers or averages of other outcomes. So what are the numbers associated with what the world is like? Here's a standard way of doing this. Let's say you run into somebody, you want to know their utility function. You let them play a game, okay? Most of the wheel on this game is actually, you're going to be okay. But then a tiny little fraction of the wheel is going to be, if it ends there, instant death, okay? Not sure you want to play that game, but just as a thought experiment for now. So, to put it a little more formally, there's a best possible outcome here, which is your life continues as it was. There's a worst possible outcome, which is instant death, and then there's everything else in between. We're kind of ignoring the fact that maybe something could make your life better, but let's assume your life is just on track, it's amazing. So all that can happen is things can get made worse, and the worst is instant death. Okay, so what you can then do is play a game like this. You run into the person and say, how about you give me $30? And they say, well, I don't want to give you $30. Well, why not? What's the utility value associated with giving me $30? Well, not so sure. What is the utility value associated with that? Well, you set up a lottery. The lottery goes between no change at all in their life or instant death. It's a bit like a robbery. I mean, you're held at gunpoint, you get to choose. But it's with a lottery in this case. So you're in this lottery, and now the question is, if you want to know what's the utility value of $30 to that person, they're going to say, you can ask them, when are you ambivalent between these two situations? You'd be equally happy to give me $30 as to play this game. There's a probability associated with that, right? Because you prefer not to give away the money. So that probability is actually corresponds to the utility value of giving up $30. Okay? So this case, let's put some numbers on it. For many people, I mean, it depends how happy you are with life and things like that. But for many people, kind of the thing would be, they'd say, I can play this game if the probability of instant death is 1 in a million, so it's 1 micromorph. But if it's higher than that, I would prefer to just give up the $30. So what that means is that continuing life as is, and if nothing had happened, you didn't encounter this juncture in life where you have to make this choice, you would have had 1, and this shows that losing $30 puts your utility function at 0.999999, 6 nines in this case. Okay, so now we have a utility value for you losing $30. And now we can do this for other things too. It could be all kinds of things. Losing your code, losing yet something else. And so that way you can get all the utility values, and then you can work with them, optimize them. We're going to be a little short on time this afternoon, so I'm going to keep going for now. Okay, you might think, is money not just utility values? In some sense, it's related. I mean, more money tends to be better. If anybody disagrees and has a lot of money, I'm sure, come talk to me. I'm happy to help you if you have that kind of relationship with money. But the lotteries, you can't just average things with money the way for utilities we know you can average, and that's the right thing to do. For money, that's not true. When you have a lottery between money, different outcomes for money, just averaging them is actually not corresponding to maximizing utility. Because when you're given a lottery between, let's say, X dollars and Y dollars, that's not to you the same as just getting the weighted average of those two. And we'll see some examples in a bit. And then there's a concept of expected monetary value, which accounts for this. I'm going to go a little fast over this slide, but people tend to be risk averse in that they prefer certainty of a certain amount of money rather than uncertainty about varying amounts of money. And so that means if you have such a preference where you prefer certainty over uncertainty, that means money doesn't exactly match with your utility function. In fact, typically it'll look something like this, where the amount of utility you associate with money is kind of growing logarithmically with the amount of money. So going from having let's say, $10,000 in the bank to 100,000 is the same as going from 100,000 to a million, same as going from a million to 10 million and so forth, roughly something like that. So then you can't just average and get the right things out. You need to look at the money amounts, compute the utility associated with that money amount, and then average the utilities, and then you can back what the money is associated with it. That's where insurance comes into play. A lot of people don't like uncertainty. If they could have $1,000 for sure, let's say their bicycle is worth $1,000, but there's a 50% chance it gets stolen, in which case they're left with nothing, then they might decide to insure their bicycle for some amount. The expected money in this situation is $500. The certainty equivalent value to you, if you were sure what you got, might be something is what you would be happy with instead of this lottery, which might be $400. And so the difference between the $500 and the $400, that's what the insurance company can charge you to ensure that you're guaranteed a certain amount of money. And so that's how insurance can make their money, by helping you and at the same time helping themselves. Why don't they have such a preference? Well, they actually live in a different part of the curve than most of us do. They handle a lot of money, and the law of large numbers kicks in, so it gets more to deterministic. And so there's several reasons there why their utility function operates differently, and you can get a win-win situation, giving up some money in exchange for certainty. Now, here's an interesting example, putting this all kind of back into a concrete quiz for you guys. Let's say you can choose between two lotteries. Lottery A, 80% chance of $4,000, 20% chance of nothing. Or Lottery B, 100% chance of $3,000, and you're always getting that $3,000, 100% chance. Okay? Who would prefer A? Okay, some people prefer A. Who would prefer B? So maybe like most people prefer B, but a good fraction prefers A. Then here's another set of lotteries. Lottery C, 20% chance of $4,000, 80% chance of nothing, versus D, 25% chance of $3,000 and 75% chance of nothing. Who prefers C? Who prefers D? All right. So remember your preferences, whether you chose A or B, whether you chose C or D. Most people prefer B over A and C over D. This slide was made before you raised your hands, and it was true here. So we're in line here with most people in the world. But look at this. If the utility of $0 is 0, let's say, because we can always shift and scale utilities, then preferring B over A means that the utility of 3K is better than 0.8 the utility of 4K. Okay? Preferring C over D means that 0.8 times the utility of 4K is better than the utility of 3K. That's scaling this by a factor 4, what you have here. So we have conflicting findings here. If you did prefer B over A and C over D, you actually are in conflict with your utilities being consistent, at least seemingly so. So what could be at play here? Well, one possibility is that we're just not rational. We're just humans. We don't know how to be rational or not that well, and so that's just what we did. Some of you maybe were rational. There's another explanation for this. Let's look at this one over here. This one is a special one. You could have been guaranteed $3,000, or you might have had a slightly lower chance for a little more money. What happens when you picked A and you get nothing? What happens is actually a lot more than the fact that you don't get any money. What really happens to a lot of people is you get no money, and as a bonus, you feel really stupid. Because you could have guaranteed yourself the money. And so a way of explaining why people would go this way while still saying that people are rational is that, well, the utility in this lottery, well, if you get this outcome over here, that utility is actually quite different from just 0. It's actually negative because you have this feeling of stupidity of having made the wrong choice. All right, I'll leave you with those thoughts. And yeah, thank you. That's it for me.